what is the importance of the IMAP mission, and what do you hope to learn from it?
So IMAP is a mission that has 10 instruments that study the bubble that our sun has blown in interstellar space that we call the heliosphere. This is our solar neighborhood. This is the atmosphere of the sun that we and all the other planets of the solar system live in. It's important for understanding why there's life here on Earth. And as we look to distant stars, understanding how our solar neighborhood affects life on Earth and maybe other planets and moons in our solar system is important for looking for life elsewhere. Also, as we go through space more, it's important to understand space weather. There's actually storms in space that can affect satellites, astronauts, and we're way behind terrestrial weather for predicting those storms. So we want to undo the underlying science that will help us better predict space weather, and that's what IMAP does.
Now, can you explain a little bit about the heliosphere? And you mentioned before it's like a bubble, but it's not an actual bubble that will pop. I know a few people, as soon as they hear bubble, that's where their mind is going to go to.
So in some ways, it's more like a balloon. The solar wind, which blows out from the sun at 1 million miles an hour in all directions, has inflated this region by pushing out against the interstellar gas that's out there in between the stars. And that balloon actually expands and contracts as the sun gets more and less active and as we pass through different regions of the galaxy. But it's always going to be there, and understanding it really helps us look at, it protects us, for example, from galactic cosmic rays, which are one of the most dangerous pieces of radiation that astronauts have to worry about. And that bubble actually helps protect us from those. So.
It really is amazing. Now, you're studying this. You're sending the IMAP probe to and please correct me if I'm not pronouncing this correctly, the Sun Earth L1 language point. Why is that location so important? Why not just send it to the boundaries of the heliosphere?
So the L1 Lagrange point is this really interesting gravitational point where a spacecraft at L1 stays between the sun and the Earth all the time. It follows the Earth around its orbit, yet it's closer to the sun. And so that allows us to see the space weather that's heading directly at the Earth. Sending a probe out to the boundaries of the solar system, the Voyagers are out there now, both Voyager 1 and Voyager 2, but it took them more than 45 years to get out there. Here we can get in 100 days, we can get to the Earth Sun L1 Lagrange point.
That's a long commute for 100 days.
It's 1 million miles, and the you have to follow an orbit around the sun and sort of track yourself in to that point. But it is 1 million miles.
Well, it's just a mere million miles. It's right in the neighborhood. Um, Now, you have 10 scientific instruments on board. Is there any one that you're the most interested in seeing its data?
So we have two instruments that are I'm really expecting to see groundbreaking science from. One of them is an instrument called CODIS, which is the compact dual ion composition experiment. We always come up with good acronyms when we can. And that's measuring a type of particle called superthermal ions, which are somewhat energetic, but not as energetic as the stuff moving at almost the speed of light, which is the instrument that I've built studies. So, but the reason why it's important is because those particles, for reasons of the physics and the detectors, are very hard to study. And this instrument is much better than any that we've previously launched. So we expect to learn a lot there because that shows how particles get accelerated from the solar wind all the way up to the dangerous energies. You have to study the part in between as well. There's also an instrument called IMAP low, which is the lowest energy of the three energetic neutral atom instruments that we've got. Energetic neutral atoms are really weird because even though they're moving very fast, normally when you're moving fast, you've lost electrons, and so you've got an electric charge on a particle. These are neutral. They've got the same number of protons and electrons, and so they travel straight the way light does. And with those, we can map out what's happening at the edge of our solar system from this place just a million miles away from the Earth. And so we get to see the area that the Voyager spacecraft are traveling through now from near Earth. And that's really cool. And we expect to see very surprising stuff from that.
That really does sound amazing. Now, just how soon, as soon as the probe gets to this location, how soon will it start running its test, and how long will this mission be?
So we are actually going to be what's called commissioning the instruments during the 100 days that it takes to get out there. By the time we get out to the L1 point, we expect to be fully operational. And as soon as we go into this pseudo orbit around L1, we're going to start sending the prime science data. So we'll be ready as soon as we get there. The prime mission for IMAP is 2 years, but we expect to last much longer than that and do great science for as long as we can.
And that seems to be the case with so many NASA satellites and probes, where the mission may be 2 years and 5 years, but then you hear something like, "Oh yeah, it's still active 15 years later, and we're still getting data." It really is amazing the type of technology that gets sent into such a harsh environment, and it lasts pretty long.
Yeah, so we do a lot of testing on these spacecraft and instruments to make sure that they work in space. And so the most dangerous part is actually getting them to launch and launching them. Once they get into space, there's radiation damage, but we've built them to handle that. And so these spacecraft tend to last much longer than their original design. Again, I'll talk about the two Voyager spacecraft, which launched in 1977, and now almost 50 years later, they're still sending data back to us. That's remarkable.
That really is amazing. Now, what's also amazing is that the IMAP mission is going to also help the astronauts of the Artemis missions, most likely Artemis 2 and Artemis 3 when we go back to the moon. What is its role in the Artemis program?
So we do the science that helps improve space weather predictions, but we're also sending data back in almost real time that tells us about solar storms heading at the Earth. Between IMAP and the two ride shares, the smaller spacecraft that are traveling along with us, Caruthers and the NOAA spacecraft called SWIFO L1, all three spacecraft are looking at space weather, storms in space. And astronauts need that. We tracked it during the Apollo days, but we're doing much better now. And all three of these instruments will improve our understanding of space weather.
How far advanced have we come to understanding space weather, solar winds, solar storms, and being able to track it? And how is IMAP and its two little partners going to contribute to that to make it better than what we know now?
So we do understand space weather a lot better than we did back in the Apollo days. Back in the Apollo days, we could observe things like particles that were coming at the astronauts, warn them if there was a radiation storm coming. But we didn't have prediction anywhere near as good as we do now. And even now, we want to get much better. But now we understand the active regions, what we call sunspots, and how they should look just before they send out a big solar storm. And we have instruments that can look at these coronal mass ejections, these enormous explosions, bubbles that blow off the sun. We can see them when they come off the sun. So that's one of the things that Caruthers, one of our two ride shares, does. So, oh, actually, not Caruthers, sorry, SWIFO L1. I got that one wrong. SWIFO L1 has a coronagraph that looks at these bubbles. Caruthers is actually looking back at the Earth. But so we have gotten better, but we've still got a long way to go to get to the point where we can understand space weather the way we understand terrestrial weather.
That is great. It's nice to see how far we're coming along. We're still looking ahead. Last question, because I know you have a time limit. From the moment that this mission was thought of until now, tomorrow we're launching. How long has this mission been, and what's the journey been like for you?
So it's been more than 10 years since I and a couple colleagues started thinking about this mission and putting together the initial proposals that said this should be an important mission to do. It's been a fun ride. Um, I've been part of it at every single step. And to finally see it launch tomorrow is going to be absolutely fantastic. It's not the first spacecraft that I've helped build that I've watched launch, but it's probably the most important. And it's certainly going to be an exciting day tomorrow.